All right, I would like to thank everybody for jumping on board here. My name is Tim Stewart. I am president at Visual Decisions. We have been in the business of providing software and services to companies to collect data from the shop floor and utilize that to drive improvements for many years now. And what I'm going to talk about today is driving quality improvements with the industrial Internet of Things, augmented reality, and machine learning. So in terms of the agenda for the conversation here, I'm going to give a quick introduction, then talk about preventing the causes for poor quality, and with a special focus on several categories. Then talk about escapes and how we can prevent escapes and how we can also deal with those that do happen and end up in warranty. I'll give some closing thoughts and then I'll take questions from the audience if there are any. So with that, I'd like to kick it off with a quote from Deming. Every system is perfectly designed to get the results it gets. And so pretty much no matter where your quality is today, it is a result of the system that you have in place. And if you want to change the results that you're getting from a quality perspective, you have to do something to change that system. And so then the question becomes, how can you change your quality system or your system overall for better results? And obviously I'm in the business of utilizing data to do that. And one of the problems with this is that data is everywhere. And it's not so much being able to get to data necessarily as being able to get the right data and find what you're looking for. So this is a bakery example, and just looking at all of the different places where you have information flowing into the systems, and where all that, what type of information is coming from all those different places can be overwhelming. And working with bakeries to identify where they have overages, where they have scrap, etc. The first thing that we had to do was to basically take a survey of all of the different data that existed, find out what we could utilize immediately, and then what the gaps were that we had to fill in order to be able to get the complete picture we were looking for. Another example, I worked with a firearms manufacturer, and they had 7 primary plants. And when I talked to IT, because the COO wanted a corporate quality dashboard, IT told me that all of the quality data was in SAP. And I kind of chuckled and said, no, it's not. And so in the end, we found 57 different systems that contained quality data. And a lot of these were redundant. So they had multiple SPC systems that they had in the different plants and so forth. But when we looked at it overall, there was just a tremendous amount of quality data out there, but there wasn't one single place that you go to find all of that information. And so, when they had something like a recall, or they had quality issue that they needed to investigate, what happened, for a particular lot when, it went through the plant, it was very difficult for them to do that analysis. When we started this, even the quality people didn't know all of the different systems that had the quality data in them. Another issue that you have to address is that most of those systems contain performance metrics. So for instance, first pass yield or defects per million or whatever it might be, those are things that will tell you if you're winning or losing. They will tell you if things are getting better or they're getting worse. What they won't tell you is if your first pass yield went from 98% to 93%, that's bad, but you don't really know why, and you don't know what to do about it. And so to get to that why and what to do, you have to start to look at the diagnostic metrics. And the diagnostic metrics, for instance, in the example here, we have cracking defects. And then underneath cracking defects, we have arc strike cracking, cold cracking, crater cracking, hot cracking, etc. And then underneath each one of those, we have actual detailed reasons why those particular cracks happened. And there are different corrective actions that we can take for each one of those different types of failures. And so if we know what's going wrong, first of all, in real time, we can hopefully address that if we can see it soon enough so that we don't accumulate bad parts. And secondly, as we see that data over time and we aggregate that data over time, we can see what are the primary failure modes for our process. And we can start to put corrective actions in place for those long-term situations. And overall, we're trying to reduce the cost of quality. So what does that really mean? It means that we have an internal cost of poor quality, which is scrap, rework, the labor for that, getting the logistics of getting bad parts, out of the system, out of the plant, and so forth. Many other costs associated with that. The cost of good quality. So how much does it cost us to do our testing, to have the process in place to produce those good parts and so forth. And so how can we reduce that cost of poor quality without spending an equal amount on inspections and so forth. And then there's the external cost of quality. So reducing escapes. Obviously anything that gets out of the plant can have big impact from a warranty perspective, from a customer relationship perspective. You can lose customers due to bad quality. You can have chargebacks depending on the industry that you're in and so forth. And so once things get out of the plant, the costs go up dramatically. And so as high as the cost of scrap and rework can be within the plant, if you allow those things to leave the plant, that external cost of quality can be even much more dramatic. So how can we start to address these things? If we look at a traditional Ishikawa diagram or fishbone diagram, it breaks it down into different cause categories, and I use one that has 6 traditional breakdowns of man or manpower, machine, method, material, measurement, and environment. And each one of these different categories can be broken down further, and you can start to look at what are the different types of failures that you have for manpower, what are the different types of machine failures that generate quality issues and so forth, methodology and so on. And what I'm going to do is I'm going to focus on those top 3 today, man, machine, and method. That doesn't mean that I can't help to address those bottom 3 with IoT and AR and machine learning and so forth. Certainly, for example, on the environment, being able to put environmental sensors in place to sense temperature or humidity or overall vibration can certainly have an impact. At Cummins Engine, when I used to work there, I worked in the fuel systems division, and we were trying to hold extremely tight tolerances on a plunge grind on the nozzle. And we actually had to rip out the floor of the manufacturing plant, put down a layer of rubber, and then lay concrete again back over the top of the rubber in order to dampen the vibrations of the trucks driving past the plant. And so there are definitely things in the environment that you have to account for. At that farms manufacturer with the bullets they were manufacturing, the humidity had to be very much accounted for as you were looking at how much gunpowder you would load into each round, as another example. And so there are definitely things that we can do in terms of putting sensors in place, putting the machine learning algorithms in place to look at, how do I change that gunpowder load based on the humidity and temperature in the ambient room as I'm performing the manufacturing. But I'm really just going to focus on those top three for today. So from a manpower perspective, what are the most common human errors causing scrap and rework? And so essentially all quality issues are the result of variation in the process. And from a manpower perspective, what are the sources of variation that you have there? It could be, they're not well versed in the standard operating procedures or standard work or work instructions for that particular process. It could be that they're new. It could be that they're just having a bad day. But one of the questions that you can really answer to get at, is manpower one of my driving factors here, as opposed to any of the other categories, is when I look at the process being run by different operators, do I have different first pass yield for those different operators? Do I have a different defect rate depending on who is actually running the process? Because if that's the case, then it's very highly likely that at least some amount of my variation is driven based on who's running the process. And if that's the case, if I can narrow it down to say that the people are having some impact on the process and the results that I'm getting, then I can start to look at why and what I can do about that. And if we start with the assumption that everybody is trying to do a good job, then what can we do to help them, and what can we do to provide them with tools that will enable them to do a better job running the process? So before I get to some of the things that we can do, let me talk about some of the things that are kind of driving that complexity for those workers. There is, first of all, a lot of turnover in a lot of workforces. We have, in many places, an aging workforce on the manufacturing floor. And as you replace those workers that are retiring with new workers, there's a skills gap. Those people that have been running the process for 30 years and just know in their bones, on a humid day, I make this adjustment to the process, kind of a thing. That should really be captured in the standard work, but it often isn't. And so a new worker comes into that process and they don't know all of those different things that aren't captured in the work rules. And then we have product and process complexity. So as products get fancier, as we start to put intelligence into products, as we start to use more advanced manufacturing techniques and so forth, there's a lot of complexity that hasn't been there in the past. So even our existing workers may not have the skills that are required in order to manufacture things underneath a new process or a new product set. And then we have continually increasing customer demands that are really driving a lot of that complexity in the product and the process. So some of the value drivers that are out there for these things are improving the workforce efficiency. How do we reduce attrition and improve the training and productivity of the workers very quickly? Increasing the quality and the yield for those workers and so forth, and then reducing the operational costs of training and compliance and maintenance as well, because all of those will eventually have an impact on the quality of the product too. So the first thing that we can do to start capturing that knowledge from that aging workforce, if you've had somebody that's been running the process for 30 years, then how do you actually capture the fact that they're making those minor adjustments underneath different conditions and so forth? And one way that we can start to do that is by utilizing the augmented reality solutions that are out there. So they can actually capture what they're doing as they're doing it. And then you can very easily enhance that video, enhance those pictures that they take of the process and so forth with work instructions, so that these are things that you could hand over to a new worker and they could very easily see all of the details behind that. It's very hard to get someone to describe in enough detail on just a piece of paper exactly what they're doing underneath each circumstance and all of the environment that surrounds them, provide enough context to be able to clearly understand those things. But if I take pictures and I take video, I don't have to use as many words, and so it's much, much easier to create that document of everything about that work process and all the steps that need to be taken to do that properly. There's also the possibility of giving remote assistance. This obviously isn't as possible in a high volume environment, but in a environment of more of a CNC type of environment where each product might take several minutes to produce, instead of if a worker has a question, instead of having to leave that process to go find someone to ask that question to, or just having them take their best guess at what it is that they should do to resolve that issue, we can actually set this up so that you can get remote assistance. And so the worker right there in the process is able to work with an engineer, work with someone else that has run this process, work with someone at corporate that has run this process, and actually show them using their phone or anything else to what that question is in front of them. They can interact on those screens and so forth, and get the assistance that they require in order to produce the good parts. And then training itself can be much more effective. And so rather than facing the choice, do I train at the machine where I now have to take that machine out of service for a period of time while I'm training the worker, or if I'm taking the worker outside of the process, but then I may not have the level of interactivity on that process to do that training as I would if I were at the machine. If we can create a virtual instance of that and allow that interactivity, allow that visualization and so forth, you can get the benefits of both, that realistic interaction with the machine, but also not tying up the machine, taking it out of production while you do that training. And so it can help with the training costs, it can help with knowledge retention, it can help with employee satisfaction, and all of these things as you're trying to attract perhaps a younger workforce, bring new people in, keep them interested and so forth. It really becomes a recruitment tool as well, because one of the things I hear from a lot of companies that I work with is that it's very hard to attract this younger generation of workers and kind of maintain their interest as they're going through the process of onboarding. And so some of these things just have that cool kind of wow factor that help you bring those people on board and keep them happy. From a machine perspective, how do we address some of those causes for poor quality from the machining? And so once again, quality issues are driven by variation. And in this case, if we're looking at variation that's caused by the machine, how can we identify, what are the factors within that machine that are actually creating that variation? And so one of the things that is out there today is you have a number of different software packages that allow you to perform statistical process control, looking at the output of the parts and so forth. So you're taking measurements of the parts and you're looking for the variation within those, and you're using all of the different rules and so forth to know when the process is out of control. But what those traditional SPC processes don't do is to tell you why it's out of control, what was the cause of it being out of control and so forth. All of that work still has to be done once you identify that it has left control. There are a lot of quality systems out there that allow you to connect to the machine itself and pull information from the machine to do that type of quality analysis. But they tend to be limited to looking at the data from one machine at a time. And it's very hard to contextualize that information that you're analyzing within those platforms or within those pieces of software. When you're utilizing an I-IoT platform, machine learning embedded within there and so forth, what you can actually do is start to analyze across different processes. So instead of just looking at the one machine, I can look downstream and I can look at what's happening to this material as it goes through multiple processes. It's also often the case that I don't have my first inspection. I don't sense the quality issue until much later in the process. And so how do I now relate that quality issue back to where the quality problem happened in the first place? If all I'm doing is pulling information from one machine and analyzing it locally there within quality software that's just looking at that machine, then it's very much impossible to do that. But if I have something that's connected to multiple pieces of hardware, including multiple testing systems and so forth, now as I start to look at what are the types of variation that I see in the product, I can start to analyze where that type of variation could have come in from the different processes that I have in place. There's additional causal analysis that you can look at that you can get by looking at the tag data. This is possible in some quality software today, but if you're just doing statistical process control, then it may not be something that you can do today. And so if I look at the input variables and the process variables, so something like if I'm cooking I'm cooking that loaf of bread that I mentioned earlier, and I want to look at what is the weight of the bread that I'm getting out of the process. And I need to make sure that I'm always over my 12 ounces of bread that I'm supposed to cook. Well, I can start to look at the variation in the bread itself, and I can start to see if I'm in control. But then I can start to look at what are the exact amounts of each ingredient that I'm putting in. I can start to look at the baking temperature. I can look at things about the mixer and so forth as I'm going through those individual processes, and I can look at those variables in real time, and I can start to correlate those with what I'm seeing on the output side from the SPC data. And by doing that, I can start to look at what are the causal factors, what are the variables that are correlated to that output. And now I can start to really zero in on those to analyze what are the things that I need to tightly control on the input and the process side in order to control the output side more closely. I can start to look at customized workflows and analysis that's tailored to the environment. So with a lot of these IoT platforms, you have the ability to really customize what that screen looks like, what you have in the workflow for doing the analysis and so forth. And depending on the different process that I have in place, what type of manufacturing I'm doing, what I'm doing, what step I'm doing within that overall process and so forth, I can really tailor the analysis to that individual process instead of just having pre-built screens that just go through set workflow. I can start to do additional contextualization of the data. And so, if I'm seeing variation coming in from the machine, it may be driven by, maintenance. And so being able to track when was my last date of, different types of preventive maintenance routines and correlate those to the performance that I'm seeing from the machine can be very important. We talked about operators earlier and being able to track how do my different functions, vary based on who's running the process and so forth. I can start to look at, are they actually adhering to the standard work or the work instructions? are they setting things up properly in the first place, and so forth. I can look at downtime data, and so one of the things that I can look at is if I'm doing machine learning on all of these things and doing predictive quality analysis, one of the first steps of doing that machine learning is to actually cleanse the data. And so if I have downtimes happening on that machine, those downtimes are often associated with a bad part being produced at that same time. So the machine goes down, the part that I'm working on when the machine goes down is damaged as a result of that machine failure. And so what I probably want to do is I probably want to factor that out of the data that I'm utilizing for my machine learning. Because otherwise, it's going to look for those, inputs, those process variables, and associate that with, a bad product. When that's not necessarily the case, it's only the case because I had the machine failure, the downtime. And so there's a lot of things that we can do around contextualization of the data that make that machine learning much more effective. And then I can also do alerting within here. So if I have that real-time process monitoring, I can start to look at alerts so that if I produce one bad part and I sense that right away, I don't continue making bad parts, because I immediately alert the operator, I alert the supervisor, whoever's responsible from an engineering perspective and so forth, with the fact that I had a bad part produced, or even that I'm predicting that a bad part will be produced based on what I'm seeing from power draw, or from a vibration analysis, or any number of different factors. So just some examples here. This is one that we did at a customer where we looked at essentially, we have some quality criteria and then different set points that we were using. And what we're able to identify from visualizing this data that we didn't see from just a raw analysis of the numbers was that there were certain set points where we were seeing pretty much all of the quality issues. And so when we look at this, for most of the set points, there was very little variation. Everything was pretty much on that one solid blue line here. But then at particular set points, we were seeing high degrees of variation in the process. And so I worked with the engineers in that case to really hone in on what was it that was causing that variation at those particular set points. And in that project, we also did an analysis to look at automating the correlation analysis between the inputs of the process variables and the output. And so, for instance, on the outlet O2, we were able to look at a negative correlation between the outlet O2 and our output variable. And by just automating that correlation analysis, where we looked at pretty much all of the different factors that we were capturing, we had over 120 different process variables that we were capturing in that process. And comparing that to the output, we were able to identify where do correlations exist. Now, any statistician will tell you correlation does not necessarily equal causation, but if I can see a quick list of the ones that are highly correlated, now I can start to do the analysis on, does it make sense that that would be a causal factor for my defects and so forth. And so once I've done that analysis, now I can start to look at, I know that this is correlated to the output. Does the variation in this process variable start to happen before I make bad parts? And if so, then I can start to utilize that in my machine learning process, in my alerting process, to let people know that I'm going to be producing bad parts based on the fact that I've got this variation happening in this process variable. So being able to automate that analysis is very useful when you have a lot of different variables in play. And especially when you're doing this analysis across multiple steps in the process and trying to figure out, okay, I've got my testing downstream and I'm seeing particular types of defects. And now I want to analyze when that set of parts went through the upstream steps, which of those steps saw variation that would correlate to that particular defect in the output. Another example is optimizing tool replacement, and this was something where we actually kind of, this was in the proof of concept phase, and we put some tools in different conditions onto the equipment, and we kind of forced different scenarios. So we took a tool that was near the end of its life, and we can see that it had a certain amount of variation. We put one that was known bad, on the equipment, and we saw massive variation in the power draw. And then we put a new tool on, and after it broke in a bit, then we were able to see that it mostly functioned within a very tight band of variation. And so what this told us was that looking at the output power would be a good signal for us to be able to identify which where is this tool in its life cycle. Another tool that I have used with customers is to really combine some of these different factors that we've been talking about so far and process and product failure modes and effects analysis. And so FMEAs have been used on a manual basis for decades in manufacturing. And for those of you that might not be familiar, typically this is done by a cross-functional team. You lock them in a conference room for days, occasionally stuff food underneath the door, and you basically list out from a brainstorming procedure for any item that you want to make or for any step in the process, what are the potential failure modes for that product or that process? And then, what are the effects of that? What are the different causes that you could have for that failure mode and so forth? And then recommended actions and so forth. And for each of these, what I'm trying to do is I'm trying to determine what is the severity of that failure, what is the probability of occurrence of that failure cause, and what is the probability that I can detect that failure. And based on the multiplication of those three numbers, I get my risk priority number. And obviously, if it's very severe and it frequently occurs and I have a hard time detecting it, then my RPN is very high. And so process FMEA and product FMEA in terms of what are the defects that I can introduce into that product can very much help direct what I'm trying to do from that IoT and machine learning perspective, as well as other types of failures that could come in, like the manpower failures that we talked about earlier. And then if I close that loop, if I start to say, well, when I collect data on what happened, why did I see a failure, what was the actual failure that occurred, if I collect that information in the same way that I've defined my failure modes and my causes for those failures, then what I can start to do over time is I can start to build up my Pareto of what are the different failures that I'm seeing, what are the failure modes, what are the causes of those failures. And so I can collect my severity information, I can collect my probability of occurrence, my probability of detection, and so forth. And I can start to automate this FMEA process, keep it evergreen. Because I may identify failure modes that I didn't do or didn't think of when I did my initial FMEA. I might change those numbers based on what I'm seeing from the actual process and so forth, as well as pulling information from warranty and everything else and utilizing that to update these numbers. And so it can both help direct the initial implementation of my Industry 4.0 project, and the Industry 4.0 project can actually keep this process up to date and keep it live. So the last cause of poor quality or category that I'm going to talk about today is methods. And for methods, what I'm really going to focus on are the work instructions, how those are delivered to the line, how those are interpreted by the workers and so forth. And so earlier we talked about training and so forth, and I probably should have put these two categories together because they're very highly interrelated. And depending on how well I've defined my standard work and how well I've implemented standard work at the line, you know, how well do I have those work instructions defined, and how well are they adhered to by, you know, my personnel out on the shop floor? Do I cover, you know, all the different scenarios and so forth? Do I have work instructions updated for, you know, individual products? How well are those accessible at the line and so forth? Do I run, you know, multiple different products one right after another? And, you know, are people able to really see, you know, what they're supposed to do for the SKU that's actually in front of them and so forth? And so if I look at those work instructions, are they clear? You know, if I talk to the workers, are they going to find them confusing? Are they able to very easily relate, you know, what they're seeing in front of them to, you know, what they're seeing in the work instructions and so forth? And then, you know, the other side of that is, how well do they actually adhere to them and, you know, follow those, that standard work? Oh, and the other aspect of it, I guess, is how much of a burden is it to update those work instructions with either new products or engineering changes, and how frequently those engineering changes or new products occur. And so for an awful lot of the companies I work with, what you'll see is, you know, one of these books. So, you know, here's the different work instructions for, you know, the different products and so forth. You have to look up the product, and then you've got a set of work instructions, you've got drawings and so forth. Some customers that I work with, this is, you know, electronic, and, you know, I've got a terminal at the station, and I can, you know, type in a part number, and I can see these work instructions on, you know, the page, and it's, you know, all in a Microsoft Word document or a PDF document and so forth. And it's still, you know, very time consuming to capture that expertise. They're often out of date, you know, with what's showing up on the shop floor, because they don't have included, you know, new products. They don't have the latest engineering changes accounted for and so forth. And it's a very difficult process to keep those up to date. It's very difficult for the workers to look at those words on the page and actually relate that to, you know, what they're seeing in front of them and so forth. And so it's hard to keep that relevant and also in front of the workers. And they have to take themselves out of the process in order to actually look at the work instructions. So even if I've got these really well done visual, you know, maybe video capture and so forth, if I have to take myself away from the machine and look at a computer terminal in order to see that video, now I have to reorient myself in front of the process and so forth in order to apply those lessons. And so augmented reality really helps to address those challenges. I talked about the easy capture, you know, earlier, but you know, here it's, as I'm looking at the machine itself, I can see those work instructions as I see the machine. So I can actually put my hands in there, and I can see my hands interacting with everything, and I can get warnings, safety warnings. I can get you know, highlights for different areas. So if I'm doing a pick and place, I can actually highlight the bin I'm supposed to pick from based on the unit that's in front of me. So there's a tremendous number of different things that I can do to really help the workers with, you know, those augmented reality solutions. Just both, not only from an offline training perspective, but as the worker is at the station and actually trying to perform the work, I can actually utilize those technologies to help them adhere to that standard work, and it's much easier to keep that standard work up to date. So just summarizing that section, I guess, um, it is very much of a boon. I've seen those tools in place. For instance, on a welding station, I've seen that augmented reality display right within the helmet, and as I'm doing the weld on the line, I can see feedback to me on the percentage complete for that weld, and I can see stats on how even I've made the weld and so forth. And so just absolutely tremendous potential for improving quality, reducing variation as an operator is doing that process. All right, escapes. For those of you that were on the phone at the beginning, I was actually planning to do a lot more on this escape section, but my weekend ended up a lot busier than I thought it would, so I didn't have quite the time to develop the section I thought. So I'll spend more time in a later webinar talking through this in more detail. But really, in terms of preventing escapes, the first step in preventing escapes is obviously produce quality parts. If I never produce a bad part, I won't have any escapes. It's just that simple. Just never produce a bad part. But assuming that variation will happen at some point, then I have to test, I have to inspect, and so forth in order to ensure that the bad parts that I do produce won't leave the plant. And so, as I look at the testing that I'm doing, if I can automate the collection of those test results and again, utilize that information as my output measurements to now correlate that information back into my process analysis, that is going to help me tremendously in improving those upstream processes. Being able to utilize advanced vision systems, and there's a whole other category of machine learning that's associated with the vision systems, and being able to utilize those to do the inspection. I worked with a manufacturer of plastic sheets, and these were very, very large plastic sheets. They were anywhere from 20 to 100 feet wide on each sheet. These things went underneath reservoirs to produce or to reduce seepage into the ground. And so when I went there initially, they had 2 workers that did nothing all day except for stand on either side of the output from the extruder and look for variations in a gray plastic sheet. And if you can imagine anything that would suck the life out of you faster than staring at gray plastic coming out of an extruder for 8 hours a day, I don't think I'd want to know what that would be because these guys just had a horrible job. And so we worked with the company to put vision system in place, and we trained it, against those workers and so forth. And we were able to get the vision system to where for the first 15 minutes of the day, the workers would do a better job than the vision system in identifying defects when they were still fresh, and maybe the first 15 minutes after lunch. But the rest of the day, the vision system actually highly outperformed the workers. And so, just had a consistent level of quality throughout the day in terms of, identifying those spots and so forth. And so then we were able to tie that vision system back into information that we were pulling from the extruder. And once again, link those together to be able to see what could we identify from the extruder that would be predictive of those bad spots that the vision system was identifying. And then, for some of these things that are, being introduced by manual methods, for things that, might not be caught in, various inspections at the end of the line and so forth. Like if I've got a complex assembly process and I've got, the multiple pick and place, and I've got, units one after the other that are different SKUs, and the operator has to know based on what item that is in front of them, which of the bins they're supposed to grab from from, very similar parts and so forth, and, put them in place. It may be something where if I put the wrong part in place, it might seat properly and my initial testing might work fine. But because, I'm putting, a different capacitor or something else in place, that unit will fail after a certain period of time in the field. And so, that's something that could completely get past any inspection or testing process. And so by putting that vision system in place, and by putting that augmented reality system in place where I, actually highlight the bins that the worker is supposed to pull from, and if they pull from the wrong bin, it actually has alarms that can go off and so forth. That can dramatically reduce some of those pick and place errors. And, there are obviously other applications of this for error proofing that can be put in place as well. So lots of different ideas on preventing escapes. Those are just a few of them. When you do have escapes and you do end up with things in warranty, then, there's a whole other process that comes into play. So most companies right now analyzing warranty data is just done on the warranty data. And so, I look at what customer had this, what geography were they in, what do I know of how they were utilizing the product and so forth, and trying to analyze, what are those factors that are most contributing to the warranty claims. Where I have smart connected products in the future or today, I can collect some of that telemetry data from that item that ended up in warranty, and I can start to look at the actual use as opposed to what the customer is reporting. And so the more I know about that usage from the field through those IoT sensors and so forth that are on the product, the more I know about whether it was used properly, whether it was used within the conditions it was supposed to be used in, and so forth. But then if I have some way of tracking that product back to the shop floor, so I know what lot number it was in, ideally there's a serial number for that item and so forth, then I can start to look at, I know that this ended up in warranty, what happened as it went through the shop floor. And all the way back, hopefully I've got the full genealogy tracking back to the suppliers, and I can look at, am I, ending up with more things in warranty from one supplier versus another? Am I ending up with more things in warranty, based on, I might be within tolerance, but for those units that are at the top end of my tolerance, I have much more of those end up in warranty. So that tells me I need to reduce that tolerance a little bit so that, those items are flagged as bad within my four walls as opposed to getting out to the customer. So there's a lot of analysis that can happen if I'm able to connect those things that are ending up in warranty back to the shop floor, and doing that same type of analysis that I've been talking about, but just, training that data, training that analysis based on the warranty information as opposed to what's coming up as bad within my own testing. So for closing thoughts, the IoT and machine learning, in my mind, are really just extensions of the existing systems that we've utilized for years in manufacturing. But just the next phase of it, one step better than what we've had in the past. For me, the augmented reality solutions are kind of a brand new lever that are now available, or is now available to manufacturers to really address some of that manpower and methodology sources of variation that were very difficult to address in the past. And being able to not only do the upfront training better and have a better delivery of work instructions and so forth, but also to do that error proofing of those manual steps based on some of those things I've talked about with the pick and place and so forth, the welding and so on, is just a tremendous lever that can be utilized, that there's just really been nothing in the past that was anything like that we could put in place in manufacturing to address those same issues. The final thing I'll mention, and I say this in every presentation, I think, but it's like a Fitbit. You if you don't change your behaviors, the Fitbit won't do you any good. Just wearing the Fitbit's not going to make you lose weight. You actually still have to change your diet, and you still have to exercise, as I've learned the hard way. And so, it's the same thing with all of these tools. People have to really behave differently tomorrow than they do today. They have to run the process differently tomorrow than they do today in order to really get the value from the tools. And so, as you look to implement these things, just keep in mind that the really important part of this is not just getting the solution itself implemented, but how am I going to work this into the standard work for the operator and the supervisor? How am I going to change how I do Kaizens, and how do I change which Kaizens I pick in the first place based on this data and so forth? How does my quality department really change what they do based on some of this new information that's available and so forth? And so those are the things that you really have to think about and make sure that you put in place in order to get the value from this. So with that, if you have questions, please type them in the Q&A or the chat right now. Or alternatively, you can email me at tim@visualdecisions.com or give me a call at 630-957-8096. All right, so let me look at the Q&A, and there aren't any questions in there. How about the chat? And nothing in the chat either. So with that then, I'll close this out and wish you all a good day, and I'll be back next week. And honestly, I can't remember what the webinar is for next week. It's been a long weekend, everybody. But thank you for coming after this long weekend, and I hope to hear from you soon. Thank you very much.